It's a great pleasure always to introduce somebody of Professor Lynn Lu's caliber when you get the opportunity to bring her to Cornell to give a talk about really her life's passion, which is to advance the renewable energy assets of this country and of the world. But it's more than that when it's somebody who's a good friend. So it's a special joy. And I hope that you saw in that last lecture of Lynn's, it was a lot of billing to live up to, I think, after what Abe said. But there was just the embodiment, I think, for the students of what we want it to see in a chemical engineer. Somebody who understands thermodynamics and kinetics, somebody who understands the importance of control, the role of processing, and of course of delivering a product, and of understanding it fundamentally. So we saw that yesterday, and I thought that was wonderful. But today we're going to see more about something that is truly going to be something very special, and that is her work on smart windows. Or, as I was reading this morning, some of the reviews that included the Wall Street Journal and a lot of other tech journals, and they said it's like sunglasses for Windows. So I hope you'll think about that when she delivers her talk. But I want to add a few remarks about Lynn's impact on the world, because not content with advancing the cause of science, doing fundamental work, she's also been very instrumental in having a presence in the world. And that's been true through her work with the World Economic Forum. She has traveled professionally to places that not many people actually stray to, like Myanmar, or as us from the British Empire say, Burma, but also to countries in Africa, and of course to Europe and in Southeast Asia. So she really has had a very visible presence around the world. I remember actually having a great conversation with her about Xi Jinping's great talk that he gave there, and of really feeling how how important it is for scientists to be out there making such an impact in the world. But she's also contributed so much to the field, and I think you saw some of that yesterday. I think you're going to see more today. That this paper that came out in Nano Energy last year is really a potential groundbreaking discovery. And so I think we're extremely lucky to be able to have somebody here with such vision and such creativity, and yet somebody who embodies all that we think a chemical engineer should be. And so with that, I'm very honored to present Lynn Lu.
the problem with this? Well, you need voltage. You don't need a whole lot of voltage, but you need voltage. And what that means is you need wires. And what that means is that it adds 15 to 20% in labor costs, which is significant. And then it really limits window operability. I mean, imagine these wires dangling around when you're trying to open and close the windows, right? And for these reasons, these big electrochromic companies have only targeted new builds, right? New builds that need to be LEED certified, right? Expensive buildings, new builds. Forget about the retrofit markets. Because how do you retrofit something when you have existing walls and you want to put wires in, right? So forget about the retrofit markets. It's new builds for now. But I would argue that the retrofit market is an important market because 50% of the buildings that are going to exist in 2050 are already around. And so that's an important low-hanging fruit that we need to think about. So we thought, well, okay, we want to get rid of the wires, but they need power. They don't need a whole lot of power. I'm biased. I like solar cells. So how about putting a solar cell right on top of the smart window? You generate power with that solar cell. Use that power to now regulate the transmission of light and heat through the electrochromic window. Well, we can look at the solar spectrum, right? So this is the solar spectrum. Visible range is 400 to 700 nanometers. So that is used for lighting. And then the near-infrared you can use for heating. What's left in the solar spectrum then? It's really the ultraviolet, right? So you need to absorb the ultraviolet light and generate power with the ultraviolet light and use that power to power the regulation of transmission of light and heat in the visible and near-infrared range. So the idea is as follows, right? You have an electrochromic window, and let's say we can make a solar cell that only absorbs near-ultraviolet light. We absorb near-ultraviolet light, and it then allows us to regulate how much visible light and near-infrared light comes through the window. So you can imagine something that looks like this, and of course you have black body radiation that's in the infrared. Well, you can take care of that by putting a low emissivity coating that's already existing right now. Okay, so that's the idea. How do we do this? Forget about using this technology, right? I mean, this technology prioritizes power generation. We're absorbing a whole lot of light. That's why it's black. But you can't use this and put it on top of an electrochromic window and expect to be able to regulate light through the electrochromic window. So I'm showing again the solar spectrum. The visible range is shaded in orange here. So for a silicon cell, silicon works so well for power generation because it has a very nice band gap. And with its band gap, it's absorbing a lot of the visible light through the near-infrared, right? And so that's how much light it's absorbing. These are some numbers just to keep in mind, right? Theoretical efficiency of silicon cells is 32%. A commercial cell is about 24%. When you put it in a module, you lose some efficiency. It's about 15%. But nonetheless, this is all to say that silicon is great when you're prioritizing power generation. It's not so good when you're trying to prioritize transparency, okay? Because it absorbs all that visible light. So again, I'm biased towards organic semiconductors, and here is where I'm going to argue that organic semiconductors is unique for this application. So organic semiconductors have specific attributes that are really suited for this application. First, it's its chemical versatility, right? And so you can synthesize and add subsequent conjugated rings to the molecule. And by doing that, you're extending the conjugation length. When you extend the conjugation length, you're changing its optoelectronic property. So here I'm showing you a series of fused benzene rings. And by extending the conjugation length, you can see that we're changing its absorption properties. And so this could be useful in making a photovoltaic cell that absorbs different wavelength of the solar spectrum. It could be useful also if you're making an LED and you want it to emit different color ranges. These are easily processable. What I'm going to be showing you is processed through the vapor phase, but you can make it so you can have an ink. And with an ink, you can coat over large areas. These are lightweight and mechanically flexible materials. So you can begin to envision these kinds of applications, right? And windows are large area applications. So this slide you saw yesterday, so these are representative chemical structures, if you will, of common organic semiconductors. Again, so this is copper phthalocyanine. It's more common than you think. It's used as a dye in the automobile industry. The point of showing you this slide is to show you this chemical versatility. And to first order, chemists know what we need to do to control or change its properties. So copper phthalocyanine is nominally a hole transporter. We can attach fluorines. Fluorines are electron withdrawing. And so as you withdraw electrons from the core, you're lowering its energy levels. And by lowering its energy levels, now this energy level is better matched with the work function of its LUMO level is better matched with the work function of electrodes. So now the fluorinated version more easily transports electrons than this guy that transports holes. Okay? This is pentacene. It's something that you can buy from Aldrich. It's an organic semiconductor. It's not soluble in any common organic solvents, so you have to use a vapor process to deposit it to make thin films. You can add these greasy side groups, okay? And when you add these greasy side groups, the same conjugated core is now soluble in common solvents like THF, toluene. You have an ink that you can coat over large areas. Yesterday, we talked a little bit about packing, and of course, these greasy side groups is going to affect the packing. But chemists to first order know how to adjust this and how to adjust the aspect ratio so you can get the right packing. This is poly-3-hexylthiophene. N is the number of repeat unit. As N increases, you're increasing the conjugated core, and so you again narrow the band gap. And then these hexyl side chains are added to again promote solubility. Right? So you can see how you can tune chemistry to get at the properties, again, to first order. So instead of using cells like this to power the electrochromic windows, you can begin to think about these kinds of technologies. So this is a slightly different technology. Nonetheless, it uses an organic dye. This is at EPFL, right? So these are dye-sensitized Gratzel solar cells. But you can see how pretty they are because they're tuned to absorb specific colors, so they're aesthetically very pleasing. Heliotech is advocating these semi-transparent solar films. You can see them there. And they can generate a small amount of energy, but again, they're not prioritizing power generation, right? They're prioritizing something else, and that something else is transparency. So we think, this is a promising class of materials for the kinds of things we're thinking about. So I'm going to tell you basically two parts that make up this story. One is the design and synthesis of these contorted molecular semiconductors to make the transparent solar cells. And then I'm going to tell you about the conducting polymers that we've used to make the smart window. And then I'm going to show you the integration of the two components to make this prototype system. And the reason I've split it up is because these two projects started out being separate projects conducted by two separate grad students. And it was them sitting in the same office one day that they came together and said, hey, we can integrate these and make a smart window. So I think it's a beautiful story of how grad students, when you put smart people together, beautiful things happen. So let me tell you about solar cells. So this is a schematic of a solar cell. So it's really a very simple device. It's a vertical device. You have two electrodes because you need to absorb light. So one of the electrodes need to be transparent. And we've chosen that electrode to be our anode. And then we've got a cathode. And then you've got two organic materials. One's a donor. The other one's an acceptor. And so these are the work functions of the electrodes. The lowest unoccupied molecular orbital, the highest occupied molecular orbital of the donor and the acceptor. So when you shine light, these are low dielectric constant materials. So you don't generate free carriers automatically like in silicon. What you generate is an exciton. This is a tightly bound electron hole pair. And so that's generated in either phases, more commonly in the donor phase. And then now this exciton needs to diffuse around until it finds an interface where there's sufficient driving force to split the exciton into free carriers. Once it splits, now you have free carriers, and now you can collect the free carriers at the external electrodes. Okay? That's how the solar cell works. So the efficiency of a solar cell, meaning number of electrons divided by the number of photons absorbed, right, is is a compound of the efficiency of all those individual processes that I was telling you about. So in order for you to get a high efficiency solar cell, absorption needs to be good. You need to absorb a lot of light. You need efficient exciton diffusion. You need charge transfer, and then charge collection at the external electrodes. So just for reference, polymer solar cells today have a record efficiency of about 15%. And these are cells about this big, okay, 1 centimeter squared. All right? So we're a ways away from silicon, even when we're trying to prioritize and maximize power generation. The way one quantifies a solar cell operation is to look at current density as a function of voltage. So you have this square curve. The squarer the curve is, the better your solar cell is performing. And this area is the power generation area. You've got an open circuit voltage. And again, to first order, we know how to tune this by the selection of the materials pair. That open circuit voltage is dictated to first order by the difference between the HOMO of the donor and the LUMO of the acceptor. And again, these are materials properties. So you can go to a library and sort of pick the materials. And to first order, if your materials behave nicely, you should be able to predict what the open circuit voltage is. You've got the short circuit current density. That's inversely proportional to the band gap of the material that's absorbing light, right? Lower band gap means you're absorbing more photons from the solar spectrum. Larger band gap means you're absorbing less of the photons from the solar spectrum. But inherently what this means is that these two quantities are coupled. Often when you optimize for one, it's at the expense of the other, okay? So keep that in mind. The other important thing to remember is for these organic solar cells, this LUMO-LUMO energy offset is important. I mentioned that you have an exciton and you need to split this exciton. So this LUMO-LUMO energy offset is what drives the splitting of the exciton. And that typically needs to be at about 0.5 EVs, okay? So those are the constraints of making solar cells. We're not the first ones to think about making transparent solar cells. Johnny Lunt's group has made transparent solar cells, but he's optimized for absorbing in the near infrared, simply because there's more photons there. And so this, again, is the visible range. And you can see this is the absorption profile. There is non-negligible absorption in the visible. So it turns out that this is a semi-transparent solar cell that's kind of reddish in color because it absorbs in the visible. It absorbs quite a bit in the near infrared. And so these are the characteristics. You get a VOC of about 0.6. And then it's 55% transparent in the visible, and then it absorbs blue light. Okay? So just to say that we're not the first ones to think about semi-transparent solar cells. We are, however, the first ones to think about absorbing ultraviolet light. Now, the reason people don't absorb ultraviolet light is because ultraviolet light is only 7% of the solar spectrum. Okay, so there's not a whole lot there, right? So as long as you're thinking about power generation, you wouldn't think about ultraviolet. But here, what we're trying to prioritize is visible transparency. And I'll show you later why we chose this ultraviolet light. Because of the wide band gap, we get actually a very high voltage. So, I mean, this is also to say, don't ask me the efficiency of my cell, right? I'm throwing away 93% of the photons, so how high can my efficiency be, right? So I'll give you another metric to think about our solar cells in a little bit. But our solar cell is low efficiency by traditional definition because we're throwing away 93% of the solar spectrum. So this work is done by Nick Davey. He worked on the solar cell component. He's a co-founder of a startup that we're working on now. Anna Hispansky is now at Lawrence Livermore. She started making these materials. And then Melda Sezin, who just recently finished up with us, she worked on the electrochromic materials, and she's now at Bristol-Myers Squibb. Okay, so this is my only synthesis slide. This also showcases my limits in how I can do synthesis. I'm very grateful for my first sabbatical stint. I spent my first sabbatical in Colin Knuckles' group in the chemistry department at Columbia University, where I learned this chemistry. And so that's to say that this series of molecules is really limited by our chemistry, right? Our chemistry skills. But Nick Davey has taken this and made a bunch of materials. We like this chemistry because it's actually super modular. In fact, if you look up Aldrich, you can buy a whole bunch of these boronic acids. And depending on what boronic acids you buy, you can make materials with different chemical functionality. Okay? You start out with a pentacene quinone, you brominate it, and then with these bromine active sites, you now add the boronic acid, and then you ring close through a photocyclization, and you get this molecule. Okay? And that's because we chose this benzofuran boronic acid. If you choose something else ends up here, and you can tune the optoelectronic properties of the compound. We also chose this chemistry because what we end up with is a molecule that's contorted. And you might say, well, wait a second. You were telling us about crystallization yesterday. A contorted molecule does not crystallize. And I would say, precisely, it does not crystallize. And we intentionally made this series of molecules so it does not crystallize for reasons that will become obvious in a little bit. Okay, so this was intentional. Okay, so this is to show you that we can tune the optoelectronic properties. So with a phenylboronic acid, we get the parent compound. We call this contorted hexabenzochoronine. This is with benzofuran, so it's tetrabenzofuran dibenzochoronine. This is tetrabenzothiophene dibenzochoronine. Okay, and you can see immediately that you can tune its optoelectronic properties. Now, this is actually fortuitous because when I went to Colin's group, he didn't have the heart to tell me that they had done some calculations to show that the calculations basically show that there are two separate pi systems, the core and then the external aromatic ring. Because it's contorted, so they don't communicate with each other. And so because they don't communicate with each other, you won't expect to be able to tune its optoelectronic properties. Of course, he didn't tell me this. And because he didn't tell me this, we made these compounds, and we showed that we actually can tune the optoelectronic properties, and there is actually communication between the core and the peripheral aromatic rings. Okay? So we can make solar cells. So these were the very first solar cells we made with these materials. So these are our donor materials. I'm just showing you both the donors here, so you know the energy levels. We paired it with C60 just because that's the quintessential acceptor, and that's a chemical structure of C60 here. And so we made a planar heterojunction device. It's a very simple device. So this is our transparent electrode. This is our donor layer, our acceptor layer, and our cathode. So light's coming in from the back, and you can measure the device characteristics. Now, to first order, this makes sense, right? Because you can see that the HOMO of CHBC is lower than the HOMO of TBF, and so we get a higher open circuit voltage. And because this has a smaller band gap, we're absorbing more light, and so you get a higher short circuit current density. The cells behave nicely. We just have very low current. Suffice to say that the compounds behave nicely. Now, if you look at the absorption, that's plotted in solid lines, or you can look at the transmittance, that's plotted in dashed lines. What you'll notice, again, this is the visible range, is that we have significant absorption by C60. Okay, so this is not a transparent cell. This is not sufficiently transparent for our application. So this told us that we needed to replace C60 with something else. And so we said, well, okay, why not go back to the same chemistry, because that's all we know. Now we change up the substituent, and we're going to add electron withdrawing substituent to lower the energy levels. So again, we can start with pentacene quinone, or we can start with a fluorinated pentacene quinone, both of which we know how to make, and you can make in large quantities. And now if you use the phenylboronic acid, you get the parent compound. If you use the chlorinated boronic acid, you can access the chlorinated compounds. If you start with the fluorinated and then you use the fluorinated boronic acid, you can access the fluorinated compound, and then you can access a fluorinated chlorinated compound. We're not very creative with our naming schemes. The numbers in front just represents how many halogens there are. So this is 8 fluorines and 4 chlorines. I'm only showing you a quadrant because the molecule the chemical structure is actually symmetric. Paulette's group helped us characterize these materials through DFT calculations, but we've also independently measured their solid state electronic properties and electronic structure. We've done solution measurements. So these are triply sort of verified energy levels now. I'll show you the energy levels here. This is the donor, the benzofuran compound. C60 is the acceptor that we had used earlier on. And then what you can see is as you add more halogens, we're stepping down in energy levels, okay, systematically. Makes sense? What was nice was you can actually quantify this, and the LUMO actually decreases by about 50 millielectron volts per fluorine you add. and by about 73 millielectron volts per chlorine you add. This is nice because now we have a design rule. If we wanted to make next generation materials, we can come back and use this as a rule of thumb to get us to where we need to get to without having to make the compounds and then quantify it, right? So now we have a library of compounds, the donors that you saw earlier on, and the acceptors that I've shown you here. We can pair things together. We decided we need about 0.5 EV LUMO-LUMO offset, so we chose TBF with 12Cl. We've made a bunch of other pairs since, but let me show you data from TBF and 12Cl. So again, this is our donor, the benzofuran compound, and then 12 chlorines on the peripheral aromatic ring of a coronine core is our acceptor. So this is Nick Davey holding one of these films up. Again, TBF and 12Cl. These are only about 20 nanometers thick. So here I'm showing you absorbance and transmittance through the visible range, and you can see that it's over 77% transmittance across the visible. So much better, right, compared to C60. And so this is a transmittance curve. Does it work? The answer is yes. So this is our device structure. It's a planar heterojunction structure. We don't get a whole lot of current, but our open circuit voltage is really high. In fact, when we first reported this, this was the record open circuit voltage that had been reported in the solar cell community, organic, inorganic, and otherwise. Again, because we're using wide bandgap materials, right? I mean, people don't think about using wide bandgap materials to do these kinds of things. So we're not getting a whole lot of current, but our voltage is really high, okay? We can pair this with other acceptors to just kind of check the behavior and make sure that it's behaving nicely. TBF is our donor. C60 was the acceptor that's colored, right? And as we pull up the LUMO level, we're opening this gap between the HOMO of the donor and the LUMO of the acceptor. And accordingly, you see that the open circuit voltage increases. We go from 0.8 with C60 to 1.5 to 1.6 with 8Cl, and we're approaching 2 today. The currents are small, but that's to be expected because we're throwing away 93% of the photons. And for those of you who are really curious about power conversion efficiency, here they are. Okay, they're not high. So they're about 1%. Okay, and the fill factor is important because it tells us about the performance of these cells. So I would argue that this is a better metric to quantify our solar cells. So the spectral responsivity, it's kind of like an efficiency, but it's an efficiency at a specific wavelength. And so you can look at the spectral power response as a function of wavelength. For the wavelength we care about at about 400 nanometers, our solar cells are about 16% efficient. It's pretty good, okay? And so this is with C60, and that's because the C60's absorption profile looks very different, right? And so it's not quite as nice as our materials in the near ultraviolet. Another way to quantify the performance of our cell is to look at the power density. And so this is basically taking the voltage of our solar cell, multiplying it by the short circuit current density. This is useful because it tells us the quality of the power that we're getting out. So you can look across these three devices with C60, with 12Cl, with 8Cl. The power densities are comparable at about 1.5 milliwatts per centimeter squared. What's different is the working voltage that you get out of these devices. With C60, the working voltage is only about 0.6, but with our cells, we get about 1.2, 1.1, and that's significant because now that you have these high voltages and the switching for electrochromic materials is about 1 volt, we can now make a single, simple junction cell and use it directly to drive the switching of the electrochromic window. Here, we wouldn't have enough voltage to drive the electrochromic switching. What you need to do is to make a tandem cell, right? So that complicates processing. You may ask, well, I mean, you're absorbing ultraviolet light. How do these cells really perform? What is their stability? And so these are some accelerated testing that we've done on the stability. So this is continuous illumination. So it's equivalent to 1 month of standard operation. The open circuit voltage is pinned, and it doesn't move. And that's good indication that we're not popping off the halogens on our material, right? If we pop off the halogens, you change the energy levels, you should see a switch in the open circuit voltage, and we never see that. You see a burn-in period associated with the fill factor, the power density, and the short circuit current density. That's not atypical. You see that in low bandgap polymer solar cells. You see that in small molecule solar cells. You even see that in silicon solar cells. So we see an initial burn-in period, but then it's pegged. It's quite stable. And we're doing extended testing now over large areas. But this is promising because it's telling us that the material is stable, our device appears to be stable. Okay? And so this is encapsulated with glass and epoxy, nothing special, and then it's tested in air. This is where the amorphous layer becomes important. Remember, we're targeting window applications, so we need to make large area cells. And for those of you who make solar cells, you know that the typical cell that you make in your lab is about yay big, right? 0.1, 0.2 centimeters squared. And then when you scale up, you run into trouble because you have pinholes, et cetera, that then shorts through, and you can't make those cells work over large areas. So for reference, if you have a low band gap solar cell, and so this was reported, they incur a 20% reduction in fill factor, 24% loss in power density when the active areas increase from 0.2 centimeters squared to 2 centimeters squared. So we wanted to circumvent this problem, and we thought, well, the best way to make a pinhole-free layer is to make everything defective, right? It's to make amorphous layers. So we sacrifice a little bit in the charge transport, but now everything's defective. There are no holes, right? There are no pinholes. There are no grain boundaries, no pinholes. And so because there are no pinholes, we can increase our cell size, and you can see that the current density as a function of voltage just lie right on top of each other. If you plot the power as a function of area, it's linear. Okay? It's really nice. And also, there's another factor that I should talk about, because, again, our cells produce so little current, and parasitic resistance scales as the current squared. So we suffer less from parasitic resistance as well. Okay? So this was a win-win situation for us. This is for the skeptics out there. I wanted to show you that our films are indeed amorphous. So this is the donor-acceptor interface. And so you can see that the interface is pristine. There's no long-range order. This is cross-section of the donor or the acceptor. And again, look at the thicknesses. They're very thin. We intentionally keep these thin because they're amorphous, so charge transport is not high, right? So you're limited by charge transport. So by keeping this thin, you can effectively extract the charges at the external electrodes. Okay, so then we got greedy, and we said, okay, 2 centimeters squared is great. But you know, if you want to really make windows, you need to make at least a 10 centimeter squared subcell, because then you can stitch 10 centimeter squared subcells together to make a module. So we said, okay, we're going to set out and make a 10 centimeter squared cell. But the electrode that we were using, which is indium tin oxide, I mean, you can't extract charges effectively with a 10 centimeter squared indium tin oxide electrode because it's just not sufficiently conducting. So we had to re-engineer the transparent electrode. So here, basically, what we have is a silver grid. And so this is a zoom-in version of the silver grid, right? And so it's a honeycomb pattern. It's not really visible to the naked eye. But this is now sufficiently conducting. And we can make cells with this. And you can see the 1 centimeter and the 10 centimeter squared cell. Again, it lies right on top of each other. So we can make a 10 centimeter squared single junction cells now. So hopefully I've convinced you that we can make these transparent solar cells. And so again, that was focusing on power generation here. So let me tell you a little bit about the electrochromic window that we've made and then how we couple them together. So this is a reminder of what we're after. So we envision something that looks like this. We've got a solar cell at the bottom and then the electrochromic window on the top, right? And so you want it to be on the same footprint. So we want to integrate it so we can get rid of external wires. So I should say that there are lots of electrochromic technologies out there: tungsten oxide, nanoparticles, polymer. John Reynolds has made a lot of polymers that are electrochromic. Jingguo Mei at Purdue has made also a lot of electrochromic materials. Here we're just using polyaniline because this is what we know best, and we've worked with it for more than a decade in our labs. But there are lots of other technologies out there. So we like polyaniline because it's a polyelectrochromic polymer. So poly here is many, and electrochromic means it changes color with electricity, right? So it's got multiple oxidation states. In its most reduced oxidation state, it's known as a leucoemeraldine base form of polyaniline. If you strip 2 electrons and 2 protons, you get to the emeraldine base form of polyaniline that's now blue. And then if you further strip 2 electrons and 2 protons, you get to pernogranuline base polyaniline that's purple. I'll show you the color contrast here. We've primarily worked with the intermediate state because now when you expose it to acids, you make this emeraldine salt form of the polyaniline that's actually electrically conducting. And so these were first generation students. Jung-un graduated in 2007. Jacob graduated maybe in 2009. But they've worked a lot on these materials for glucose sensing applications. So we've used this as a redox coupler in glucose sensors. We've also used this as strain gauges because it's piezo resistive. But I'm going to focus on the electrochromic side of things today. So this is the leucoemeraldine base form of polyaniline, and this is the pernagranulin base form of polyaniline. So the most reduced and the most oxidized forms of polyaniline. I'm showing you here the solar spectrum. Again, the colored region is the visible region of the solar spectrum. And you can see this is the absorbance. So sorry, I'm switching between absorbance and transmittance. But it's not absorbing a whole lot in the leuco base form of polyaniline, right? So it's transparent to the naked eye. And then in its pernagranulin base form of polyaniline, it's absorbing in the visible. It's also absorbing in the near infrared. So the idea is when we're in this state, we're blocking visible light and near infrared light from coming into the building. And when we're in this state, we're letting in light and near infrared into the building. Okay, and so this is just to show you switching, but this is with an external power source, just so that you see the color contrast, right? The color contrast is quite nice. This is also with a liquid electrolyte, by no means a window, but I wanted you to see the color contrast. And then let me quantify the color contrast now. I'm plotting percent transmittance. This is in the visible, and percent transmittance in the near infrared. And you can see nice contrast, right? 40% to almost 100%. So this is near, this is very transparent, and then this is very dark, both in the visible and in the near infrared. We can cycle this back and forth, back and forth, back and forth. It's very stable. And so the idea, again, is to couple our transparent solar cell with one of these electrochromic windows. And so the makeup of our electrochromic window is as follows. We've got polyaniline, and we need a counter electrode, right? I've said that we're shuttling electrons back and forth, so we need a counter electrode that can accept electrons when we're shuttling it out of polyaniline, and we need one that can actually spit out electrons when polyaniline wants its electrons back. So we chose P.PSS, this is a common conducting polymer, because they're complementary, meaning that when polyanilin's reduced, P.PSS needs to be oxidized, and both turn out to be transparent, so you can enhance the transparency of your window. You need the electrolyte, because you need a way to shuttle the electrons back and forth. And then, of course, when you want the dark state, when polyaniline is oxidized, P.PSS needs to be reduced, and both are in the dark state, so it enhances the contrast between the colored state and the bleached state of our electrochromic window. So this is to show you the contrast between the colored state and the transparent state of our window. This is, again, switched by our transparent solar cell now. And so you can see the contrast is quite nice in the visible range. Here we're using an ion gel, simply because when you make a window, you don't want a liquid electrolyte, right? Just in case it leaks, it's going to go all over the place. So this is a solid, it's a gel. And it's really with silica, so it's very simple. Because we have this high voltage, and the contrast is now proportional to voltage, we can actually access very high contrast. So this is to show switching with our solar cell. And you can, again, switch back and forth, back and forth, back and forth. It's nice. The one thing that's nice about electrochromic technology is that once you pulse it to the right oxidation state, you don't need to maintain that voltage in order for it to stay at that state, okay? But it's going to slowly decay. So what it means is occasionally you have to pulse it again to get it back to whatever state you want to get it back to. But you don't need a continuous supply of power in order to maintain it in its oxidation state. So this is to show the pulse. So we decided that, we need to pulse it every 15 minutes to maintain contrast. So that's not a big deal. This is to show you the electrochromic window that's powered by our solar cell. So here the electrochromic window is 2 centimeters, and the solar cell is about 1.4 centimeters, and you can see the switching. We've enhanced the speed so you can see the switching more clearly. This is to show you transparency as a function of time and the current that's required. And from these kinds of curves, we can calculate the energy requirements. So it turns out, like I said, electrochromic technology does not require a whole lot of power, but it does require power. So with our technology, with this polyaniline technology, you need about 0.4 joules per centimeter squared for 24 hours. That's including switching every hour plus this pulse every 15 minutes. Okay? Not a whole lot. And it turns out that our solar cell generates an order of magnitude more energy per unit area over the hour. And so that's good news for us because that means that if we have a simple storage device, we can store the excess energy. So when it's a cloudy day or when it's snowing like it's doing now, right, you can still operate your window. Or when you're in a city and you want to block out lights at night, you can still operate your window. Nick and I have started and Luca Technologies to basically integrate the battery to figure out how to scale this up because we think this is super exciting. We're excited about it. So where are we going from here? So polyaniline is nice because it's got multiple oxidation states. So we think we can access all these different oxidation states. So you can have a cool mode, for example, where you're blocking near infrared but letting visible light in. You can have a bright mode where you're letting both visible light and near infrared light into the building. Or you could have the dark mode, right? So you can imagine a bright summer day or a bright winter day. You might want to operate in one of these modes. So that's what we're working on. And this is the initial data to show you that you can switch back and forth between all these oxidation states. This is the dark state. This is the half oxidized, half reduced state. And this is a completely transparent state. And you can go back and forth quite nicely, both in the visible and in the infrared. Okay. So with that, I hope I've shown you a vertically integrated project. We were responsible for the design and synthesis of the molecules, so we're super proud of that, especially being a chemical engineer, right? And then to fabricate and basically integrate the device components into a system. So this chemical versatility of organic semiconductors is super important. It's given us access to a family of compounds that have tunable optoelectronic properties. We've deliberately chosen an amorphous active layer. This is really kind of perverse if you think about it because everything about organic electronics is making things more crystalline, but I think this has really helped us in this case in being able to make large area cells. And so we've seen scalability of power production. And then finally, this solar cell can effectively drive the switching of this electrochromic polymer over the same footprint. So with that, let me acknowledge Nick Davey, who worked on the Smart Windows project, and Melda Sezin, who is responsible for the electrochromic polymer and the electrochromic windows. I'd like to thank you all for your attention. Thank our collaborators, past and present, on campus, off campus, Paulette's group, the folks at Chess who've helped us with some of the characterization. And thank you for your attention.
Questions for Professor Lowe?
I don't understand yet how you switch because if the light's on, the solar cell's creating power, that would seem to actuate the electrochromic layer. So do you have some electronic logic or built in?
Yeah, so you would need to build in a simple switch. So we haven't done that quite yet. So the idea, I mean, right now we're using a solar simulator, right? So you turn on the solar simulator, you turn off the solar simulator. But what we would need to do is to design a simple circuit that has a switch and we don't even really need a battery. What we need is a simple capacitor and build that in on the side. And that would allow us to store the excess energy. And then we would be able to do the switching. And so the idea is to be able to then do this, have it wirelessly talk to your phone, and you can switch from your phone and things like that.
And would you, being committed to organic electronics, do these next steps also with organics, or would you move to little bits of silicon somewhere?
You weren't convinced when I was telling you about the attributes of organics? But I think that, so the transparent solar cell, no question about it. We'll stay with the organics.
The little bit of logic or...
Oh, the logic. Oh, yeah. I mean, the logic's going to be silicon. It's cheap. It's easy. We don't need anything very fancy, right? I mean, whenever we talk to circuit engineers, they're like, oh, this we can do with an intern. So I said, okay, let's do it with an intern. So, yeah. Susan.
Very nice. I was wondering if there might be some interesting application where you might want a pattern to emerge, and if you could instead of just having on or off,
Yeah.
you could somehow
Yeah,
make
yeah, yeah.
something appear a sign.
Yeah. So
Something
we
like that.
talked to John Reynolds' group about this. I mean, here we're showing this because we're limited in the electrochromic material. So if you imagine an electrochromic material that changes color, but the counter electrode is always opaque, right? You can now make a sign because then you can just pattern it, and that patterning would be just photolithography would be very simple, and then you can now do this pretty easily. So he's encouraged us to think about that. We're also, we were told that window applications and architectural applications are really, really challenging because, windows need to last 30 years. And so how do you prove that your technology is going to last 30 years? And so we have been encouraged to think to start small. So like automobile windows, right? So car windows, for example, those are smaller. Are those opportunities? So we're thinking about those as well. And then greenhouses, right? Anything that prioritizes transparency could be attractive. Or I mean, right now we're saying, transmission of light and near infrared for lighting and heating purposes, but also for privacy applications, right? So we're encouraged to think about a lot of these different things. I mean, really kind of, it's a realm that we haven't ventured into previously. So I mean, we're talking to lots of people, and Nick is involved in a FedTech program sponsored by the NSF, and so he has to interview 100 customers, and so they're giving us a lot of suggestions.
Does it have to be either black or see-through, or can you do?
So for this window application, I think it needs to be gray or black because I think, I mean, imagine if you were the customer and I said, oh, would you be willing to, if it's tinted, is red okay, right? I mean, so I think it needs to be, for this specific application, it needs to be color neutral.
Student question.
I was wondering, do you have any estimates on the cost of how much it costs to produce these windows for a certain area? And
So-
how that compares to the standard window you buy?
Yeah, well, I mean, you can't compare to the standard windows, and that's why I think what we need to think about are laminates that can address the retrofit market, right? So if you can buy a laminate that you can actually put on your own, that is substantially lower cost. Current electrochromic windows out there by Sage and View Glass are about $100 per square foot. It's a lot. And 20% of that is because of the wiring. We think we can make ours for less than $5 a square foot, so that cuts the 20 to 5, but that's still, I mean, it's still a lot. I mean, so if you compare us to window glass, we are not competitive. And there are a bunch of things we still need to work on. For example, removing indium tin oxide, going to a cheaper transparent electrode, things like that. But yeah, I think the long-term goal is to make laminates and films that you can just laminate on window for retrofits.
Yes, I have a less technical and more question about the pedagogy and directions of research. It seemed like there were a few areas that were almost paradigm shifts in thinking that had to happen. The amorphous versus going for crystalline. The way you even put metrics on what you're doing. Did those just fall out immediately?
No.
From the work,
It makes a good story.
Thank you.
Well, I mean, look, we've been working on crystalline materials for a long time, and so it was sitting I was sitting with the students and going, okay, how do we make it more crystalline? How do we make it more crystalline? And then finally, I was like, well, why do we need to make it more crystalline if we can make the film sufficiently thin? And that's why, if you notice, we've moved away from solution processing as well. If you solution process, it's good, it's cheap, but it doesn't get you to 20 nanometers precisely. And so we had to go with vapor deposition. And so there are trade-offs that we made, and those were made along the way, right, through iterations and things like that. Yeah.
A lot of modern skyscrapers have a lot of glass on them.
That's
What
right.
fraction of that glass is smart windows?
Right now,
Yeah.
a very small fraction. I mean, the Kimmel Center in Philadelphia, that has smart windows in it. And then there are a number of big projects that have them. Again, they are LEED certified, so they're driven by sustainability, not cost, right? I mean, if cost comes into the equation, we're done right now. Yeah. Yes, John?
So what was Colin Knuckles missing? Because he's a pretty smart character. What was he missing about the core and the
Well, I mean, those were calculations. Mike Steigerwald did those calculations and showed that there were 2 pi systems. So I don't know. I don't know.
So do the molecules move if you do like dielectric relaxation? Because I wondered if that was the thing that they're.
I don't know the answer to that, but the glass transition temperature of these materials are pretty high.
Okay, so they're glassy.
They're they're amorphous and glassy. Yeah. I mean, you can get them to crystallize, and so I didn't show you the data of getting them to crystallize. And so we spent, Anna Hispansky spent the better part of a year trying to make solar cells with crystalline materials of these guys. So she intentionally induced crystallization. And we could make cells, but they're always shorted, right? Because they're pinholes, they're grain boundaries. So you couldn't ever make them big. So.
One last question.
So I do get the, say, blocking the heat application and lighting application. Say on a sunny day, you would want your window to be a bit more opaque. But what about, say, the heating application? So consider, say, a day like today in Ithaca. When there's no sun, would it be really useful to have?
Well, there's infrared, right? So you let the infrared through, right? You can't generate heat with so this technology doesn't make heat, right? It's just whether it lets in heat or not, right? And so I think the way we argue it is occupant comfort, right? Is reducing the heating and cooling loads within the building. Yeah. So you can't make more, but you can cut how much you use.
Like how frequently would the heating scenario be feasible?
Sorry?
How frequently would that heating scenario be feasible?
The heating scenario, I don't understand it.
Like where heating would be useful. As in you would have sun outside to heat things up.
Oh, solar. Talking about solar heating through the window.
Oh, solar
Greenhouse.
heating. Oh, yeah, like greenhouses, right? So solar heating, yeah. Nowadays windows have this low emissivity coatings. You can get them with low emissivity coating. It's to block the black body radiation. And so it's really that near infrared portion that's not being blocked right now. So I think, again, it's as with any energy technology, it's not a single solution that's going to solve the world's problem. It's going to be a portfolio. And anything you can shave off energy demand is a good thing, right? And energy efficiency, in my opinion, is the lowest hanging fruit. And is sort of the wedge that people frequently ignore. And I think it shouldn't be ignored. Yeah.
I think in the interest of time we should leave it here, but we must thank Professor Liu for inspirational talk.
Thank you.